No, this is more bias in the theoretical machine learning sense. What I'm saying is, do you understand how it generalizes? Which has a lot to do with statistical bias, but it's more of a theory on how do you get what they're doing that's different. I'll pretend these pictures somehow convey meaning. I don't know if they do. And hey, maybe let's say I visualized it. I visualized the bias. There, now I've knocked off 2 of them. How are we going to do, let's do sparsity. That one's pretty easy. When do sparse vectors occur? Is anybody taking the natural language processing class right now? No one in here is? You are? Okay. How many documents are there in the world that use every single one of the 60,000 common words in the English language? Not too many of them, right? I mean, that wasn't a really well-formed question, but pick a random document. How many of the English words does it use? Probably not all of them. It's very common to represent words by counting up the number of occurrences of each word in the English language, and then using that as a big vector to represent the document. But if you learn in that respect, you have a whole lot of vectors that look like this. 1, 3, question mark, question mark, question mark, question mark, 3, question mark, question mark, question mark. Where question mark might be a 0, or it might be a I don't know because I haven't measured it, or something like that. How does one feed these things into a neural net? I don't know either. You kind of can't. Well, you can. I'll talk about this in my class. I guess I won't cover that here. Here's what you do. You guess. Pick a value for it all. You feed it forward. You see how bad your error is. Then you backpropagate, and then you update these values until it is as happy as it can be. And then you've kind of filled in the missing values. How does one do that with KNN? So here's kind of an interesting way of looking at it. Here's 2 points. What's their distance? Well, it's that, right? Well, here's a point, and here's a line. What's their distance? Probably the shortest distance between them, right? Why a line? Isn't a line just a point with one of the dimensional values undefined? Okay, so here's a point, and here's a plane. Pretend this plane is coming off of the board or something, so there's some distance between that point and the plane. You kind of can measure the shortest distance. Do you see that with missing values you can still measure the distance between 2 things? What if you have a line and another line, and pretend they're not on the same z-axis, so there's some distance between them? You can measure the distance between them, right? Well, if you can do that, then you can handle vectors that have missing values. A common thing to do, though, is to penalize the missingness, because if you do that, an unfortunate thing happens. The vectors that are the most sparse, you know the least about, they end up being the closest together. And so the one thing you know nothing about ends up being the label that you assign to everything, which obviously murders KNN. So a good thing to do is whenever there's a question mark in your vector, you replace it with some kind of penalty, like you just say that adds a distance of 1 or n to the whole thing. So we'll say we covered that. Just do it. Okay, I said some words. So terrible. Why make a chart if you're going to put no information in it? I'm going to put an X to indicate we covered it. There we go. Oh, there's something else that should be in there. We got to talk about categorical versus continuous. Cat versus continuous. How do you do continuous values in KNN? It's just normal. How do you do categorical values? Hamming distance. How do you mix them? You just do. And then you weight the axes. And then there's a whole thing about how you got to do Mahalanobis distance. Okay. I'll call that good enough for now. How do you make neural networks incremental? And what do I mean by incremental? Yeah, I mean online learning. I mean, there's a stream of data coming at you, and every time a new bit of information comes into you, you want to learn from it, and your model should get a little better, and you have to use your model right now. You can't wait till all the data comes in and then train it. So the usual approach, supervised learning, says wait till all the data comes, train, then predict. By incremental, I mean stream or learning, yeah. Now you can make anything incremental by just gathering up training sets and then retraining. But presumably that takes a lot of time and is expensive. especially with neural nets. But neural networks are just naturally incremental. We know this because I provided a train incremental method to you, right? And you used it and it worked, and let's put an X there. That one's really easy. How do you make KNN incremental? Suppose and you'll have to if you're going to do this inverted pendulum test that I want you to do with your KNN implementation, right? Yeah, so all you need is an infinite amount of storage, and every time a new point comes in, just throw it in your pile, right? And because you've got a KD tree, logarithm of infinity is pretty much reasonable, right? Well, that's almost true, right? I mean, if by infinity I mean really, really friggin' large, logarithm of really, really friggin' large is pretty much reasonable.
And you could also like...
And in fact, just to illustrate that, I'm going to claim it will never stop being true. And here's why. Natural logarithm of x, I'm going to plot it. Obviously, as x gets bigger, y gets bigger, right? But the more bigger we get, the more true it is. I'm zooming way out here and zooming out again. You see what I'm getting at here? Now that's a pretty vague, wimpy proof, but I'm going to claim that assuming your data gets huger and huger, but your computer gets a little bit faster and a little bit faster, that little bit faster is more than good enough to deal with the insane growth of data as long as you have logarithmic time. Because that's a plot of logarithms. Logarithms flatten out more and more the bigger you get. Anybody disagree with that? Therefore, KD trees, while lame for small data, are pretty darn awesome for great big data. Let's suppose you want to make your KNN learner incremental. What do? But let's suppose you don't have infinite storage space. You want to limit it to, say, 10 gigabytes. Summarize the point?
Yeah. Cluster it.
You could cluster it? Yeah, so imagine this is your KNN table and data starts coming in. What if, once you reach a certain point, you just start dropping points? Like, pick a random point and drop it when you add a new point. Will that work? I think that's a reasonable approach. There's probably better approaches, but that's one thing you could do. If you just start dropping points when new ones come in, nice thing about that is it also allows the thing to evolve, right? If over time the distribution changes, as long as your backlog of history isn't too long, it'll go away and you'll start to evolve to fit the new data points. So that's one way you could implement QTable with KNN. Another thing I found I did when I implemented a QTable with KNN is I found the points tended to come in like this. Do you see why? Because the points are coming in every time I sample the video game that I'm learning from. Well, if you start dropping random points, then these start getting sparser until eventually they're all over the place, and that's a good thing. I fiddled for a long time with how to make this incremental in a way. What I wanted to do is when I sample like this, I wanted it to ultimately end up collecting data and remembering it kind of like this. See what I'm getting at? I wanted it to remember every nth point. And I fiddled with how to make it do that for a long time, and here's what I finally came up with. I say, if the kth neighbor, if the distance to the kth neighbor is greater than some threshold, then drop the first neighbor. Here's why that works. Imagine you drop the first neighbor if the first nearest neighbor is too close. What will happen? As you're learning here, you'll keep dropping the first nearest neighbor, and each time you add a point, it'll drop the one you just did. And so its memory will kind of chase you. Let me illustrate a little better. I add a point. When I add a new point, I say, oh, that one's too close, so I erase it. When I add another point, I say, oh, that one's too close, so I erase it. And when I add another point, I say, oh, that one's too close, so I erase it. See how it's not working out the way I wanted it to? Whereas, if I start adding points, the kth neighbor is not going to be less than the threshold. I'm fixing a bug right now. Because I'm saying the distance to the kth neighbor, if it's too close. I don't want too much density in one area. Well, that's not going to happen until I've got at least k points. And when I finally do, then I drop the point that's closest and store my next point. And then the kth neighbor is not going to be less than t until I've got k points again, and then it's going to drop one. And so I end up doing this kind of a thing. And I can make t smaller and smaller until it starts incrementally learning the way I want it to. Okay, I've never seen that published anywhere, but I figured it out, seemed to work, something good to do if you want to make k and n incremental. I think we've covered that one. Oh, drat, I'm out of time. Should I cover collaborative learning? I guess I will next time. Then we'll be done with k and n. And do you feel like you get k and n at a high level? It's a pretty simple algorithm. Oh, I also got to do I didn't cover unsupervised version of k and n. So we got to do density estimation and collaborative learning with k and n. Then we'll be done with that topic. Thanks for coming. Go code it up and see you next time.